Now, this is the second question. The temperature of a piece of mass 9 gram is raised from 10 degrees Celsius to 110 degrees Celsius when it absorbs 108 joules of heat energy. Determine the specific heat capacity of the metal in joule per kilogram per Kelvin. Now, we know that we have to bring out the parameter. That is very important, right? So the solution is going to be the temperature of a piece of mass 9 grams. So meaning that they've given us the mass to be what? 9 grams. So let us bring it out. Bring out the parameters. Very important. So the mass is equals to 9 grams, right? But remember, we are not going to work with gram. We are going to be working with kilogram. So we have to divide this gram by 1000 to have kilogram. So if you divide 9 by 1000, what are you going to have? You can use your calculator to do that. But here, I'm going to do it here. So that is, if I say 9 divided by 1000, I'm going to have something like this. 1, because I have 3 zeros, I'm going to count backward 3 times. So I'm going to have 1, 2, 3. So that is going to be 0.009 kilogram. So I'm going to have my mass to be 0.009 kilogram. So now let us continue with the question. Remember, the temperature of a piece of mass 9 grams is raised. We have written out the mass is raised to from 10 degrees Celsius to 110 degrees Celsius. So meaning that we have to calculate the temperature rise, right? So our temperature rise, which is delta T, we can calculate that it's going to be T2 minus T1. So which is going to be what? 110 minus 10, which is going to give us what? 100 degrees Celsius. So that is the temperature rise, right? Now, when it absorbs 108 joules of heat energy. Now, joule, what is that parameter that has the unit of joule? The heat quantity of heat itself has this unit. So meaning that this time around, they've given us the quantity of heat. So Q is equals to 108 joules. So it is very important to be able to identify each unit, each parameter, and their unit. Very important. So determine the specific heat capacity of the metal. Now, they're asking us to determine the specific heat capacity. We know that C, which is the specific heat capacity, is what of the metal is what we don't know right now. So it is very clear now that we are still going to make use of our normal formula for calculating the quantity of heat supplied, which is Q is equals to mass times specific heat capacity times temperature rise. If a body is heated, is gaining heat, we are going to use that formula. If a body is losing heat, to know the quantity of heat loss, we are still going to use the same formula. So our Q here, we are going to write out the formula. Q is equals to MC delta T. That is the formula to calculate what? To calculate the quantity of heat. But this time around, we are looking for C. We are looking for the specific heat capacity of the metal. Now, there are two things. It's either you substitute each of these into the formula, or you make your C that you are looking for the subject of the formula, meaning that you make your C stand alone. So now, let us try to make the C the subject of the formula so you understand what we mean by that. So since we are looking for C, which is the specific heat capacity, what is disturbing C is M and delta T. So let us use that to divide both sides so that specific heat capacity can stand on its own. So meaning that I'm going to divide both sides. I'm not going to waste time. I'm just going to divide both sides by, since I'm looking for C, so this and this should go, but they can only go by division. So I'm going to say divided by, but I'm going to divide both sides by M delta T. So divide this one too by M delta T. Do you know why? this M will cancel this M, and this delta T will cancel this delta T, so that we can have only C to be equals to what? To be equals to Q over what? M delta T. This time we say that C is now the subject of the formula because it is standing alone now. So all we need to do now is to put, anywhere we have Q, put 108 because Q is 108. So I'm going to say 108 divided by, then anywhere we have mass, we put 0.009. So we have 0.009 times delta T, which is the temperature rise, is going to be 100, right? So which is going to be 100. But here now, please, you can use your calculator to do this, and you're going to get the final answer straight away. But now I'm going to use, I'm just going to use and to solve this, and then look, I'm going to deal with what I have here. So 0.009 times 100 can just be like shifting this decimal point 2 times because I have 2 zeros. I'm multiplying by 2 zeros. I'm multiplying by power of 10. So this is 1, 2. Then I'm going to have 0.9, right? So the 100 is gone like that. I'm going to have 0.9 and the 100 is gone. So I'm going to have 108 divided by 0.9. Don't forget, I said when you multiply 0.009 times 100, you're going to have 0.9. So divided by 0.9 now. You see, all of this does not really matter. You can use your calculator to do this and you're fine. So now, having done that, then you need to simplify this. 108 divided by 0.9. Remember, 0.9 itself can be 0.9 itself is the same thing as 9 over 10. 0.9 itself is 9 over 10. Yes. So here now, I'm going to rewrite this here now, which is going to be equals to, so my C is going to be equals to 108 divided by this 9. 0.9 is 9 over 10. So it's as if I'm writing something like this: 108 divided by 9 over 10. And I hope you can still remember, that your rules of division of fraction. This is fraction. So the division is going to turn to this multiplication, but this fraction will turn upside down now, which is going to be 10 over what? Over 9. So what are we going to have at the end of the day? So C is going to be equals to what? 9 in 10 is going to give us 1, right? So 9 in 10 is 1. Remember 1, put it here, making what? 18. Making 18. So how many 9 are we going to see in 18 now? It's going to be 2, right? So times this 10. So this is going to give us 12 times 10 is 120. But remember, this is specific heat capacity. Don't forget your unit, joule per kilogram per Kelvin. So I'm going to put 120 joule per kilogram per Kelvin. So our C finally is 120 joule per kg per Kelvin. That is the solution to that.